What if I told you that smaller AI models could actually beat the big guys? And what if we could make AI think more like a human, step by step, to solve even the trickiest problems? That's the kind of mind-blowing stuff we're diving into today on AI by AI.
Exactly. We're unpacking some seriously cool research that's pushing the boundaries of what AI can do. First up, we'll explore how to make AI models smarter during testing, a technique called test time scaling. Think of it like giving your brain an extra boost right when you need it most.
Then we're turbocharging image and text generation with Show Turbo, a faster, more efficient way for AI to understand and create content. We'll break down how it works, even if you're not a computer scientist.
Next, we're tackling AI speed with hierarchy drafting. This is all about making AI inference, that's basically AI thinking, way faster by organizing information in a smart way. Imagine having a super organized filing system for your brain.
After that, we're leveling up AI's math skills with ReasonFlux. This framework helps AI break down complex problems into smaller, more manageable steps, just like we do. It's like giving AI a structured thought process.
Finally, we're exploring CODEI, a method that trains AI to predict code inputs and outputs, teaching it to reason more effectively. Think of it as learning by example, but with code. So buckle up, because we're about to unlock some serious AI potential.
Let's dive into this paper. Can 1B LLM surpass 405B LLM? Rethinking compute optimal test time scaling. It's a mouthful, but the core idea is super interesting. Can we make smaller language models perform as well as, or even better than, massive ones by being smarter about how we use computation during inference?
Exactly. So they're tackling test time scaling, or TTS. What's the basic concept there?
TTS is all about using extra computation power after the model is trained during the actual task-solving phase. Think of it like giving the model extra time to think and refine its answers. There are two main flavors, internal and external TTS. Internal TTS trains the model to think slowly using chain of thought, while external TTS uses methods like sampling or search to improve reasoning with a fixed model.
Okay, so it's like giving the model a chance to double-check its work. What specific questions were the researchers trying to answer?
They focused on two big questions. First, what's the best way to scale test time computation across different types of models, process reward models, PRMs, and different levels of problem difficulty? Second, how much can this extra computation actually improve performance on tough tasks, and can smaller models really beat larger ones this way?
Process reward models. That sounds important. What are those?
PRMs are essentially models that evaluate the reasoning process of another model. They give a score or reward to each step in the reasoning chain, guiding the model towards better solutions. It's like having a tutor that gives feedback on your work as you go, not just at the end.
Got it. So the PRM helps the main model refine its thinking. What were some of their key findings?
The big one is that the optimal TTS strategy really depends on the policy model. That's the main LLM doing the task, the PRM you're using, and how difficult the problem is. And here's the kicker. With the right TTS strategy, a tiny 1B parameter model can actually outperform a massive 405B parameter model on challenging math problems.
Whoa, that's a huge claim. How did they test this?
They ran experiments on Math 500 and AIM-24, which are tough math problem datasets. They used PRMs ranging from 1.5B to 72B parameters and policy models from 0.5B to 72B. They found that smaller models could even beat state-of-the-art models like O1 and DeepSeek R1 with the right TTS approach.
So it's not just about throwing more parameters at the problem. It's about being smart about how you use the resources you have. What are some of the TTS methods they looked at?
They considered best of n, which generates multiple responses and picks the best one, beam search, which explores multiple possibilities at each step, and diverse verifier tree search, DVTS, which is like beam search but with more diverse exploration. They didn't look at methods involving look-ahead operations like Monte Carlo tree search because they found them inefficient.
Okay, so different ways to explore the solution space. The paper mentions compute-optimal scaling. What's that all about?
Compute-optimal scaling is about finding the perfect set of hyperparameters for a given TTS strategy to maximize performance on a specific problem given a certain compute budget. It's like tuning the knobs on your model to get the best possible performance for the resources you have.
And they found that this optimal scaling is reward-aware. What does that mean?
That's a crucial point. They realized that the PRM's rewards heavily influence the generation process. If the PRM is biased or inaccurate, it can lead the model down the wrong path. So they propose a reward-aware strategy that takes into account the specific PRM being used, the prompt, and the reward function itself. This makes the TTS strategy more adaptable and effective.
So it's not just about the model's size or the amount of computation, but also about the quality of the feedback it's getting. What about problem difficulty? How did they handle that?
They moved away from using quantiles to define difficulty because different models have different reasoning abilities. Instead, they used absolute thresholds based on pass-at-one accuracy to define easy, medium, and hard problems. This gives a more consistent measure of difficulty across different models.
That makes sense. So what are the practical implications of all this? Can we really ditch the giant models and just use smaller ones with clever TTS?
Not quite, but it's a step in that direction. The paper shows that TTS can significantly boost the performance of smaller models, making them competitive with and sometimes even superior to much larger models. It also highlights the importance of choosing the right TTS strategy and PRM for the task at hand. It's about efficiency and making the most of the resources you have.
So it's a call for more research into smarter inference techniques rather than just blindly scaling up model size. What were some of the limitations of the study?
They mainly focused on mathematical tasks. They suggest that future work should extend TTS to other areas like coding and chemistry. Also, they want to explore even more effective methods for compute-optimal TTS. There's still a lot of room for improvement and discovery in this area.
Definitely sounds like a promising direction. It's exciting to think that we can achieve better performance with smaller, more efficient models by focusing on smarter inference strategies.
All right, let's dive into this paper on Show Turbo. It's all about making multimodal models faster, specifically focusing on image and text generation.
Multimodal, meaning it handles different types of data, right? Like images and text together?
Exactly. And Show, the model they're improving, is pretty cool because it can do both text-to-image and image-to-text tasks. But the problem is, it's slow. It takes a lot of steps to generate anything, which makes it expensive to use.
So Show Turbo is trying to speed things up. How do they do that?
They've come up with a clever trick. They treat both image and text generation as a denoising process. Think of it like cleaning up a blurry image, but for both images and text.
Denoising. So they're starting with something noisy and gradually making it clearer?
Precisely. For images, Show uses something called discrete diffusion, which is like adding noise and then learning to remove it. For text, it's usually generated one word at a time, which is slow, but Show Turbo uses a parallel decoding method where it refines multiple words at once.
Parallel decoding sounds much faster. So how does this denoising idea tie everything together?
They use a technique called consistency distillation, or CD. The idea is to train the model to map any point in the denoising process to the final clear result. So even if you start with a really noisy image or text, the model can quickly jump to the clean version.
Okay, so CD helps it skip steps. But how do they make sure the model doesn't just give up and output the same thing every time?
That's where regularization comes in. They add extra training objectives to make sure the model still learns to generate diverse and meaningful content. For example, they make sure the model can still predict the next word in a sentence, even while denoising.
Got it. So CD speeds things up, and regularization keeps the output interesting. What about this trajectory segmentation and curriculum learning they mention?
Those are tricks to make the training process smoother. Trajectory segmentation is like breaking the denoising process into smaller chunks, so the model can focus on learning consistency within each chunk. Curriculum learning means starting with easier tasks and gradually increasing the difficulty. which helps the model converge better.
So does it actually work? Is Show Turbo faster and still good?
The results are pretty impressive. For text-to-image generation, Show Turbo can generate images in just 4 steps that are better than the original Show in 8 steps. And for image-to-text, it's about 1.5 times faster without losing much accuracy.
That's a significant speed-up. What about the quality of the generated content?
They used several metrics to evaluate the quality, like Genieval, HPS, IR, and clip score. These metrics measure things like how well the generated images match the text descriptions and how much humans prefer them. Show Turbo consistently scores well on these metrics.
So it's faster and still produces good results. Any downsides or limitations?
They mention that there's a slight performance drop in image-to-text tasks, implying a trade-off between speed and accuracy. Also, they found that a technique called classifier-free guidance, or CFG, which is often used to improve image quality, isn't as necessary with Show Turbo, which is a bonus because CFG adds extra computation.
Interesting. So, by unifying the denoising process and using techniques like consistency distillation, trajectory segmentation, and curriculum learning, they've managed to significantly speed up multimodal generation. Sounds like a solid step forward.
Definitely. And the fact that it's open source makes it even more valuable for the research community. It'll be exciting to see how others build upon this work. Okay, let's dive into this paper about accelerating large language models, or LLMs, using something called hierarchical drafting. It's all about making these models faster without sacrificing accuracy.
Sounds good. LLM inference speed is definitely a hot topic. So what's the core problem they're tackling?
Basically, LLMs are slow because they generate text token by token. This paper focuses on speculative decoding, which tries to generate multiple tokens at once. The trick is to draft potential tokens and then verify them with the actual LLM. If the drafts are good, you get a speed boost.
Ah, I see. So it's like having a faster, less accurate model propose some text and then the big LLM checks if it's right. What's hierarchy drafting, or HD, then?
Exactly. HD is their new drafting strategy. Current methods either need a lot of fine-tuning or don't work consistently across different tasks. HD organizes different sources of tokens into a hierarchy based on temporal locality.
Temporal locality? What's that in this context?
Think of it as how likely a token is to reappear soon. Some tokens are very specific to the current context, like numbers in a math problem. Others are common phrases that the LLM uses all the time, and some are just statistically common in language. HD puts these into different databases based on this locality.
Okay, so different databases for different kinds of tokens. How does that actually speed things up?
During drafting, HD checks these databases in order, from the highest to lowest locality. So it starts with tokens most likely to be relevant to the current context. This increases accuracy and reduces the time it takes to find good draft tokens.
That makes sense. So what are these different databases they're using?
They have 3: context-dependent, model-dependent, and statistics-dependent. The context-dependent one stores tokens specific to the current generation process, like stuff from the input prompt. The model-dependent one has phrases the LLM frequently uses across different generations. And the statistics-dependent one contains common phrases from large text datasets.
Got it. So it's like a memory hierarchy, prioritizing the most relevant and frequently used tokens. What kind of speedups are we talking about?
They tested it on something called SpecBench using LLMs with 7B and 13B parameters. HD outperformed existing methods, achieving robust inference speedups across different model sizes, tasks, and even temperature settings.
Temperature settings? How does that affect things?
Temperature controls the randomness of the output. Higher temperatures mean more diverse but potentially less accurate text. HD still works well even with higher temperatures, which is a good sign.
Interesting. So it's not just faster, but also more consistent. What were the limitations of previous approaches that HD is trying to solve?
Existing methods often require fine-tuning smaller models to act as drafters, which is expensive. Or they modify the LLM architecture itself, which also adds overhead. Database drafting, which HD builds on, avoids these parameter updates by pulling draft tokens from databases. But previous database methods relied on a single source, leading to inconsistent performance.
So the key innovation here is using multiple databases in a smart way. What about the drafting latency? Doesn't searching through databases add overhead?
That's a crucial point. Adding more sources to a single database increases latency. HD minimizes this by using the hierarchical framework. The databases with higher locality are smaller, so they're faster to search. They start with the fastest, most accurate database and only move to the slower ones if needed.
Okay, that makes sense. Start with the quick wins and only go deeper if necessary. So what are the key takeaways from their experiments?
HD consistently achieves significant acceleration gains compared to other lossless methods. It's robust across different tasks and model sizes. And the hierarchical framework adaptively selects the appropriate database for each task while minimizing draft latency.
Sounds like a solid improvement. Are there any downsides or limitations to this approach?
They mentioned that they didn't test it extensively on LLMs larger than 13B parameters. They expect it to work even better on larger models, but that's something for future research. Also, the sources for the databases aren't entirely new, but the focus is on how they're organized and accessed, making it easy to integrate new sources in the future.
Right, it's more about the architecture than the individual components. So overall, it's a promising approach for speeding up LLMs without sacrificing accuracy or requiring extensive retraining.
Exactly. It's a practical solution that leverages readily available data resources to improve LLM inference speed. All right, let's dive into this paper on ReasonFlux. It's all about improving how large language models, or LLMs, reason, especially when tackling tough math problems.
Sounds interesting. So what's the core idea behind ReasonFlux?
The main idea is hierarchical reasoning using what they call scaling thought templates. Basically, they've created a system that breaks down complex problems into smaller, more manageable steps, and then uses predefined templates to guide the LLM through each step.
Okay, so it's like giving the LLM a structured problem-solving framework. What are these thought templates exactly?
Think of them as high-level strategies or patterns for solving specific types of problems. The paper mentions a library of around 500 of these templates, covering various mathematical concepts. Each template includes a name, tags for easy searching, a description of the underlying principle, the scope of problems it applies to, detailed application steps, and even examples.
So instead of the LLM starting from scratch, it can pull up a relevant template and follow its guidance. How does it choose the right template?
That's where the hierarchical reinforcement learning comes in. They train the LLM to plan an optimal template trajectory, which is essentially a sequence of templates that will lead to the solution. It's like creating a roadmap for problem solving.
Reinforcement learning? Got it. So the LLM learns which templates work best for different types of problems through trial and error. What about the inference scaling system they mention?
That's how ReasonFlux adapts to the complexity of the problem at hand. It dynamically scales the thought templates during inference, meaning it can retrieve a series of high-level templates and perform reasoning in stages. This allows for a better balance between exploration and exploitation, leading to more efficient problem solving.
Exploration versus exploitation. That's key. It's about finding the right balance between trying new things and sticking with what works. So, how well does ReasonFlux actually perform?
The results are pretty impressive. On the math benchmark, it achieved 91.2% accuracy, surpassing OpenAI's O1 preview by 6.7%. And on the Amy benchmark, it solved an average of 56.7% of problems, outperforming O1 preview and DeepSeek V3 by a significant margin.
Wow, those are some serious gains. It sounds like ReasonFlux is a significant step forward in improving the reasoning capabilities of LLMs, especially for complex mathematical tasks. What's the significance of the structured template library?
The structured template library is crucial for efficient and accurate retrieval of relevant knowledge. It addresses the scalability challenges faced by traditional retrieval-augmented generation systems, where searching through unstructured text corpora can be difficult. By organizing the templates with metadata like names and tags, ReasonFlux can quickly find the most appropriate templates for a given problem.
So it's not just about having a lot of information, but also about organizing it in a way that's easily accessible and usable. The paper also mentions hierarchical reinforcement learning. How does that work in practice?
The hierarchical RL process involves two main stages: structure-based fine-tuning and preference learning on the thought template trajectory. First, a base LLM is fine-tuned on the structured template library to understand the content and intended use of each template. Then, the model learns to plan a sequence of high-level thought templates for an input problem, associating each step with the most relevant template from the library. The effectiveness of a given trajectory is measured by the average accuracy achieved by an inference LLM across similar problems, which serves as the reward signal for refining the navigator model.
That makes sense. So the model learns to not only understand the templates, but also how to string them together in the most effective way. What about the inference scaling system? How does it adapt to different problem complexities?
The inference scaling system involves a multi-round interplay between ReasonFlux, the structured template library, and a downstream inference LLM. Given an input problem, ReasonFlux analyzes the core mathematical concepts and configures an optimal template trajectory. It then retrieves the most relevant thought templates from the library and instructs the inference LLM to instantiate each step with problem-specific details. The results are evaluated by ReasonFlux, which decides whether to refine the trajectory or retrieve alternative templates. This iterative feedback mechanism allows ReasonFlux to dynamically adjust the template trajectory based on the problem complexity.
So it's a dynamic process where the model is constantly evaluating and adjusting its approach based on the intermediate results. That sounds like a much more efficient way to solve complex problems compared to traditional methods. What are some of the key takeaways from this paper?
The main takeaways are that hierarchical LLM reasoning via scaling thought templates can significantly enhance complex reasoning capabilities, outperforming state-of-the-art models on challenging math benchmarks. The structured template library facilitates efficient retrieval and adaptation of relevant knowledge, and the hierarchical reinforcement learning enables LLMs to generate optimal thought template trajectories. The inference scaling system allows for dynamic adaptation to problem complexity, achieving a better exploration-exploitation trade-off for robust and efficient problem solving.
This ReasonFlux approach seems like a really promising direction for improving LLM reasoning. I'm curious to see how it evolves and what other applications it might have beyond mathematical problem solving.
All right, let's dive into this paper. Can 1B LLM surpass 405B LLM, rethinking compute optimal test time scaling? It's a mouthful, but the core idea is super interesting. Can we make smaller language models perform as well as, or even better than, massive ones by being smarter about how we use computation inference?
Okay, so instead of just throwing more hardware at the problem, we're talking about optimizing the process. What's test time scaling, or TTS as they call it?
TTS is all about using extra computation during the inference phase. That's when the model is actually generating answers or predictions. Think of it like giving the model extra time to think through the problem. There are two main types: internal, where the model is trained to think slowly using chain of thought, and external, where we use methods like sampling or search to improve reasoning with a fixed model. This paper focuses on external TTS.
Got it. So external TTS is like giving the model a set of tools to work with while it's trying to solve a problem. What are the key questions they're trying to answer?
They're really focused on two things. First, what's the best way to scale test time computation across different models, reward systems, and problem difficulties? Second, how much can this extra computation actually improve performance, and can it really let smaller models beat larger ones?
And what did they find? Did the little guys actually win? Wow, that's a huge deal. So it's not just about size, it's about how you use what you've got. What's driving these improvements?
A big part of it is something they call reward-aware compute optimal, TTS. Basically, they realize that the reward system you use to guide the model's search process is crucial. Previous methods used a single process reward model, or PRM, as a verifier. But this paper argues that you need to consider how the reward function interacts with the model and the problem itself.
Okay, so a PRM is like a judge that evaluates the model's reasoning steps. What's the issue with using just one PRM?
The problem is that PRMs can be biased. If you train a PRM on one model's outputs and then use it to evaluate a different model, you can run into out-of-distribution issues. The PRM might give inaccurate rewards because it's seeing reasoning steps it wasn't trained on. They found that the reward significantly affects the generation process and outcomes. Some PRMs favored short responses, leading to incorrect answers, while others produced correct answers but used way more tokens.
So the reward function needs to be tailored to the model and the task. How do they account for problem difficulty?
That's another key point. Previous work used quantiles to group problems into difficulty levels, but the authors found that this wasn't effective because different models have different reasoning capabilities. Instead, they used absolute thresholds based on pass-at-1 accuracy. That's the percentage of times the model gets the right answer on its first try. They defined easy, medium, and hard problems based on these thresholds.
Makes sense. So they're adapting the TTS strategy based on the model, the reward function, and the problem difficulty. What specific TTS methods did they look at?
They focused on 3 main methods: best of n, or BON, which generates multiple responses and then selects the best one; beam search, which explores multiple paths simultaneously; and diverse verifier tree search, or DVTS, which extends beam search by dividing the search process into multiple independent subtrees.
And how did these methods perform with different models and problem difficulties?
They found that the optimal TTS method depends on both the model size and the problem difficulty. For small models, search-based methods like beam search tend to outperform BON, while for larger models, BON is often more effective. And for problem difficulty, BON is better for easy problems, while beam search works better for harder problems, at least for smaller models.
So it's not a one-size-fits-all solution. You really need to tune the TTS strategy to the specific situation. Did they look at any biases in the PRMs themselves?
Yes, they identified several issues. PRMs can be overcritical, assigning low scores to correct steps. They can neglect errors, giving high scores to steps with clear mistakes. They can have error localization bias, penalizing steps that aren't actually where the error occurred. And they can have scoring bias, favoring certain response lengths or being sensitive to voting methods.
Those biases could really throw off the search process. So what's the big takeaway here?
The main takeaway is that compute optimal TTS is a powerful way to improve the reasoning performance of language models, especially smaller ones. By carefully considering the policy model, the PRM, and the problem difficulty, you can achieve results that rival or even surpass much larger models. It's all about being smart about how you use your resources.
Definitely sounds like a promising direction for making AI more efficient and accessible. Thanks for breaking it down.
All right, let's dive into this paper. CODEI, Condensing Reasoning Patterns via Code Input-Output Prediction. Sounds like a mouthful, but the core idea is pretty neat. They're trying to improve reasoning in large language models, or LLMs, by training them on code. But not just any code. Code transformed into a specific input-output prediction format.
Okay, so we're talking about reasoning here. Why is that such a big deal for LLMs?
Reasoning is fundamental. It's what allows LLMs to go beyond just regurgitating information and actually solve problems, make inferences, and adapt to new situations. The paper highlights that while LLMs are getting good at tasks like math and code generation, thanks to lots of training data, they still struggle with other reasoning domains like logic or scientific inference because the training data is sparse.
That makes sense. So how does code come into play here?
That's where CODEI comes in. The authors argue that real-world code contains a wide range of reasoning patterns. Think about it. Code involves logic, decision-making, and problem-solving. So they propose using code as a training ground for these reasoning skills.
But wouldn't training on raw code just make the model better at coding? How does that translate to general reasoning?
Exactly. That's the key innovation. They don't just feed the LLM raw code. Instead, they transform the code into this code input-output prediction format. Basically, they take a piece of code, turn it into an executable function, and then ask the model to predict either the output given an input or a feasible input given an output. And here's the kicker. They want the model to explain its reasoning in natural language using what's called chain of thought or CODEI rationales.
So it's not just about getting the right answer, but also explaining why that answer is correct. That sounds like it could force the model to actually think through the problem.
Precisely. By predicting inputs and outputs and explaining the reasoning in natural language, the model learns to disentangle the core reasoning flow from the specific syntax of the code. It's learning universal reasoning primitives like logic flow planning, state space searching, and decision tree traversal.
Okay, I'm starting to see the picture. So they're creating a data set of code snippets, input-output pairs, and natural language explanations. How do they actually build this data set?
They start by collecting raw code files from various sources, including a large collection of Python code called CodeMix and a subset of Python Edu focused on complex reasoning tasks. Then they transform these files into a unified format. This involves cleaning the code, extracting the core logic into functions, adding a main entry point, and creating an input generator.
An input generator? What's that for?
The input generator is a Python function that creates non-trivial inputs for the code, following the requirements of the main function. It uses randomness, but within constraints, to generate lots of different input-output pairs for each function.
So they're automatically generating a ton of training data. That's smart. But how do they get the natural language explanations, the CODEI rationales?
They use another strong LLM, DeepSeek v2.5, to generate those. They give it the function, the query, and either the input or output, and ask it to explain how to derive the correct output or a feasible input.
And what about this CODEI thing? What's the plus plus all about?
That's where it gets even more interesting. Because they're working with code, they can actually verify the model's predictions by running the code. If the model gets the wrong answer, they don't just throw it away. Instead, they give the model feedback, like incorrect answer or the actual output based on the incorrect input, and ask it to try again. This multi-turn revision process is what they call CODEI O++.
So it's like a teacher giving a student feedback and letting them revise their work. That's a clever way to improve the quality of the training data.
Exactly. And the results are pretty impressive. They tested CODEI O and CODEI O++ on a bunch of different reasoning tasks, and they found that it consistently improved performance across the board, not just on code-related tasks, but also on things like logic, math, and common sense reasoning.
That's a strong claim. Did they compare it to other training methods?
Yep. They compared it to several strong data baselines, including WebInstruct, OpenMathInstruct2, and even just training on raw code. And CODEI O consistently outperformed them, delivering more balanced and generalizable reasoning abilities.
So the key takeaway here is that transforming code into this input-output prediction format, and then training LLMs to explain their reasoning in natural language, is a really effective way to improve their general reasoning abilities.
That's the gist of it. It's a clever way to leverage the structured nature of code to teach LLMs how to think more effectively. Well, that about wraps it up for today's episode. It's been a whirlwind tour through some fascinating corners of AI research, hasn't it?
Definitely. It's amazing to see how much innovation is happening and how many different approaches researchers are taking to push the boundaries of what's possible.
It really is. I think one of the biggest takeaways for me is that size isn't everything. We saw how smaller models, when combined with clever techniques like test time scaling, can actually outperform their much larger counterparts. It's a testament to the power of efficient algorithms and smart resource allocation.
Absolutely. And it's not just about efficiency, but also about quality. The work on ReasonFlux, for example, showed how structuring knowledge and guiding the model's reasoning process can lead to significant improvements in accuracy, especially for complex tasks like math.
Right. Giving AI a structured thought process, breaking down problems into manageable steps. It's almost like teaching it how to think like a human. And then there's the work on CODEI O, which is taking a completely different approach by leveraging code to improve reasoning abilities.
Yeah, that was fascinating. The idea of transforming code into an input-output prediction format and then training the model to explain its reasoning in natural language, it's a really clever way to distill the essence of reasoning from the specific syntax of code.
And let's not forget about Show Turbo. Speeding up multimodal generation without sacrificing quality is a huge win, especially as we move towards AI systems that can seamlessly handle different types of data.
Definitely. And the hierarchical drafting approach for accelerating LLMs is another great example of how we can make these models more efficient without sacrificing accuracy. It's all about organizing information in a smart way and prioritizing the most relevant tokens.
It's exciting to think about where all of this is heading. We're seeing a shift towards more efficient, more adaptable, and more human-like AI systems. And who knows what breakthroughs are just around the corner.
Exactly. It feels like we're just scratching the surface of what's possible. Thanks for another insightful conversation. Until next time.